Greetings everybody, and today we're going to be coming up with a very nice generalization for this integral using the Dogbone contour from complex analysis, which I have gone through in a previous video. Link up here or in the description to check that out. But this is the integral from a to b of x minus a to the pth power times b minus x to the 1 minus pth power, where a and b are real numbers, and of course a has to be less than b for this integral. And the interesting thing is this p, because it can be anywhere between minus 1 and 2, non-inclusive of the endpoint. The integral will converge for all those p values, but we're just going to exclude 0 and 1 because in the final result for this video, I guess, it's actually not defined at 0 and 1, but you can take the limit and things will work out that way anyways. But yeah, we can just consider p to be between minus 1 and 2, and it should work out. So this integral is a very nice generalization. You can solve many integrals that are of this form just by plugging in the numbers into the generalized formula. And as I said before, we're going to be using the Dogbone contour, and if you've watched my previous video on that, you'll know that the branch cuts are a little bit tricky to get your head around, and we're going to be going through that first. So step 1 of this video is we're going to be investigating some branch cuts. So in order to study the branch cuts, let's first define for ourselves some kind of complex function f of z that we're going to be contour integrating around, and we're just going to take this integrand and replace all the x's with z. So we're going to have z minus a to the pth power, then b minus z to the 1 minus pth power. And what I want to do now is I want to write this in polar form because we want to investigate the argument of this function. So in order to do that, let's turn everything into base e. So first of all, we have e to the pth power, and then since we're bringing the z minus a up to the top, we take the natural log of z minus a. Then same deal for the second factor, we're going to have e to the 1 minus p, and then natural log of b minus z, like so. Alright, and now what I wanted to do now is expand out each of these natural logs, because whenever we have the natural log of a complex number, it's equal to the natural log of the absolute value of the complex number, so that's the real part. And then you also add on I times the argument of that complex number for some chosen branch of the argument function. So let's do that. Now we're going to get e to the p, and then natural log of the absolute value of z minus a. And then we're going to have I times the argument of z minus a, but because we're distributing this p into everything, let's add I times p times the argument of z minus a. And then we're going to do the same deal on the second factor, so 1 minus p times the natural log, absolute value of b minus z, and then we're going to add I times 1 minus p times the argument of b minus z, like so. Next, let's split up these exponential functions a little bit. We can use the additive identities for the exponential function, if that's what it's called. So you can just split the exponential function up like so. And so notice on this factor and this factor, we can reduce things down a little bit, because if you imagine moving this p up to the top using the natural log properties, you'll have e and natural log which will cancel each other out, leaving us with z minus a to the pth power. And same deal over here, we have b minus z and then raised to the 1 minus pth power. Alright, and this is actually the modulus of the function f of z, which is quite nice. Now let's take a look at the argument. So we're going to have e to the I, which is going to be a common factor on both of these factors. And then since we're kind of multiplying these two exponential functions, we're adding the arguments. So we have I and then p times the argument of z minus a, and then plus 1 minus p times the argument of b minus z, like so. Alright, very nice. And notice that we basically have it in polar form. We have the modulus, we have the argument or the angle, and the nice thing is the modulus is always continuous. It won't make any jumps or anything as you move around the complex plane, but what will have some discontinuities is the arguments, because it depends on what branch of the arguments you're going to take, and that's what we're going to take a look at now. So let's erase this section. We're going to stick this argument at the top because we're going to be using it later on as well. Alright, cool. And we basically want now to investigate some of the arguments or what branches we should take for these two argument functions, because they're going to be completely different because they come from two separate natural logs. So let's take a look at the arg of z minus a first of all. Let's imagine we have our complex plane here, and I'll grab myself a different colored marker. Let's say our a value was over here. The branch line of arg of z minus a will be some line that's centered around this point A. And what we want to do is we want to define it somehow so that the branch line lies directly facing the negative real axis, like so. So this is the point A. And then we want to do the same thing for the arg of b minus z as well. We want to define it, let's say b is over here. We want to define it such that the branch line also is directed towards the negative real axis. And the idea is, if we manage to do this, then we can actually show that over the interval minus infinity to a, our function is actually continuous, and we're just left with this branch cut, this finite branch cut between a and b. And that's what we're going to be constructing our Dogbone contour around later on. But for now, let's try to come up with some branches for these two arguments function. So for the arg of z minus a, this is pretty straightforward. We can just take the principal argument, so we can let minus pi be less than the arg of z minus a, and this is less than or equal to pi. And then we can also let, for arg of b minus z, now this is a little bit more tricky, but since we have a minus z, we're kind of reflecting everything. So it looks as though we're going to be also between minus pi and pi, but because we want to reflect everything, we need to imagine it's going the other way, so between 0 and pi. So we're going to have 0 less than or equal to the arg of b minus z, which is less than 2 pi. So something like that will work out nicely. And now what we're going to be doing is we're going to be showing continuity across the interval minus infinity to a using these branches of the arguments function. So first of all, let's consider the interval minus infinity to a, and we want to show that our function is continuous across that interval. So in order to show continuity, we need to show that when we approach it from above, it's the exact same argument or angle as if we approached it from below. And since our function f of z, the argument of our function f of z, is dependent on the arg of z minus a and the arg of b minus z, we have to consider what happens as we approach above on each of these arguments separately. So first of all, let's take a look at arg of z minus a. What would happen as a complex number approaches the interval minus infinity to a from above? Well, we know z is an element of that interval, which means z minus a, well, we just subtract a from everything over here, would be on the interval minus infinity to 0. And if we call this complex number w, let's take a look on the w plane, for example. Then on minus infinity to 0, which is this section over here, you can clearly see that the argument of all the complex numbers there will approach positive pi because we're approaching everything from above. So arg of z minus a will approach pi, and as for arg of b minus z, it's going to approach, now this is a little bit more tricky to think about, but we know z is going to end up on minus infinity to a, which means minus z is going to end up on minus a to positive infinity, which means that b minus z will end up on b minus a comma infinity. And notice that b is greater than a, which means that let's call this complex number w. If we look on the w plane once again, b minus a to infinity will start at some positive real number, b minus a, and then we're considering all the points that go up to infinity over there. And if z is approaching from above, that means the imaginary part is initially positive and reducing. But over here, since we have a minus z, our imaginary part is in fact going to initially be negative and reducing. So on the w plane, our imaginary part is negative and reducing, which means as z approaches from above, w will approach from below, and the argument will end up being 2 pi. So this is what happens from above. Let's see what happens from below. So from below, arg of z minus a. Well, again, if you look on that picture, as you approach from below, you're going to approach minus pi, and arg of b minus z Well, let's just use the picture we have here already. If it's approaching from below, that means our z will have a negative imaginary part, which is reducing. But because we have a minus z over here, the imaginary part of w will initially be positive and reducing. So if it's initially positive and reducing, we're going to go to 0, an angle of 0. All right, so we have all these pieces of information. Let's combine them together. So for the case where a complex number approaches from above on the interval a to b, arg of f will be equal to, let's see, we're going to have a p times the arg of z minus a, which is pi. And then we're going to add 1 minus p times the arg of b minus z, which will end up being 2 pi. And then as for below, arg of f will be equal to, well, we have p times arg of z minus a, which is minus p times pi. And then b minus z, arg of b minus z approaches 0, so that just kills off everything over here. And in fact, the nice thing is, these two things are actually congruent mod 2 pi. Because if your argument is congruent mod 2 pi, then you're going to end up with the exact same complex number, and we can show this quite easily. Let's suppose p pi plus 1 minus p times 2 pi is congruent to minus p pi, mod 2 pi. That means, let's expand things out a little bit over here. So p pi, let's actually add p pi on both sides. So 2p pi plus 2 pi minus 2p pi is congruent to 0, mod 2 pi. And you can clearly see that 2p pi and minus 2p pi, or 2 pi p in that case, will cancel each other out. And we're going to be left with that 2 pi is congruent to 0 mod 2 pi, which is obviously true. So in fact, these two arguments over here will produce the same complex number. So hence we've just shown that across the interval minus infinity to a, we're going to be continuous. So that's quite nice. So now let's do the exact same thing for a minus b, because we're going to be needing those argument values later on. Of course, you can see it's going to be discontinuous because we have one branch cut over here. So it's not really going to cancel with anything. But let's do the exact same process. So now let's consider the interval a to b. So arg of z, what happens from above actually? So above, arg of z will approach, well, z is going to end up on a to b, which means z minus a. This should have been arg of z minus a. Z minus a will end up being on 0 to b minus a, which if you call that w, so if you call this w over here, will be some small section over here maybe, and if you're approaching this from above, then the argument will approach 0. So this is going to approach 0. And as for arg of b minus z, what is this going to approach? Well, z is on a to b, which means minus z is on minus a to minus b, or actually minus b to minus a, which means b minus z will be on 0 to b minus a, so the exact same interval over here. But again, we're approaching from above, which means we have a positive imaginary part which is reducing. Because we have a minus c, we're going to have a negative imaginary part that's reducing in the w plane, which means that we're going to be approaching an angle of 2 pi. So 2 pi over here. And as for the below, what are we going to get? Well, arg of z minus a, again, that's going to approach 0. And arg of b minus z, that is going to approach, well, you look at this picture once again. If approaching from below, we have a negative imaginary part that's reducing. Because we have negative, on the w plane, we're going to have a positive imaginary part that's reducing. So it's going to reduce down to an angle of 0. So that's quite nice. Let's combine all these together and figure out the argument of f of z. So arg of f will approach. Now we're going to have p times arg of z minus a, which is 0. So we're just left with 1 minus p times 2 pi from this part over here. And over here, arg of f, both of these are 0, so it's just going to approach 0. Alright, very nice. And I guess we'll just draw some arrows on this picture. As we approach from above on the interval a to b, we're going to approach an angle of 1 minus p times 2 pi. And as we approach from below, we're going to be approaching an angle of 0. And we're going to be needing those two values later on. Right, so we're basically done with this step 1, which is the branch cuts. Let's now do step 2. And step 2 is just going to be constructing the contour. We're going to be integrating around. We already know we're using the Dogbone contour, so it's nothing too special. So we have the complex plane. Probably won't draw the vertical axis actually. So let's just consider the real axis and the rest is the complex plane. Let's say we have 2 points A and B over here. Well, our Dogbone contour will look something like this. We have the two lines that are parallel that go above and below the real axis. We have the branch cut over here, of course. So this is the branch cut between A and B. And we connect these two paths by constructing some circles on each end. Now it looks like a dog bone, kind of. And we're going to call this whole entire contour over here C. And we're going to be traversing in the positive direction, which is anti-clockwise. We're going to call this top path psi 1, the bottom path psi 2, the left circular path gamma 1, and the right circular path gamma 2. And our contour C is just the union of all those paths, so we can write out a couple of integrals. We can say that the contour integral over C of f of z dz is going to be equal to the integral over psi 1 plus the integral over psi 2 plus the integral over gamma 1 plus the integral over gamma 2. And the way we're going to be calculating each of these integrals on the right over here is by using some parameterizations and whatnot. And the way we're going to be calculating the integral over C is by using the residue at infinity, because what we're enclosing a branch cut, so we can't really use the residue theorem. So if we blow up this contour, imagine you have some bicycle pump and you blow it up, then what you're going to get is you're going to get a very big contour like so. That's also traversed in the positive direction. And let's call this contour gamma. So this contour integral will also be equivalent to the contour integral over gamma of f of z dz. And to calculate the integral over gamma, we can just use the residue at infinity, which I've derived in a previous video. You can check up here or in the description for that. Alright, cool. So we know that this integral we can use the residue at infinity, but there's just one small catch with that. We have to be in the negative direction. So let's reverse the direction of this contour. So we're going to introduce a negative up here. That's the notation I like to use to indicate negative direction. And in order to counteract that, we need a negative outside the integral. And then now this is going to be minus 2 pi I times the residue at z equals to infinity of our function f of z. So if you want to know where all this stuff comes from, then as I said before, check out the residue at infinity video which I made. Alright, cool. So we basically have the construction for our integrals, and we basically know how to evaluate this thing now. We just have to calculate each of these separate parts. I guess let's put this back up over here. So the residue at z equals to infinity, or in fact minus 2 pi I times the residue at z equals to infinity of f of z is going to be the sum of all these integrals over here, which is what we're going to be calculating now. So I guess I'll leave this picture, hopefully we'll have enough space. But first of all, let's calculate the integrals over psi 1 and psi 2. So the integral over psi 1 of f of z, so this is step 3 now, which is integrals. So integral over psi 1 of f of z dz, we can parameterize this by introducing new substitution. We're going to let z be equal to, now notice on psi 1 we're basically on the interval a to b, not quite there, but we can just imagine we're taking the limits and consider the interval a to b, but it's kind of raised up a little bit by some kinds of epsilon over here. So we're going to have a t plus I epsilon, and then t is going to vary between b and a. So it's going to start at b and then end at a, and that from this parameterization you're going to get the set of all the points that are on this path. And of course our differential dz is going to be the same thing as dt. Alright, now if we plug all this in, we're going to get the integral from b to a of f of z, but f of z, let's just plug this in. So we're going to have z, which is now t plus I epsilon, and then minus a to the pth power, and then b minus z. Now z is t plus I epsilon again, to the 1 minus pth power, and then dz is going to be equal to dt, like so. And now remember, we can write our function, well, this is more or less f of z over here in polar form, so let's do that. This is now equal to, I'm also going to change the orientation of that integral by introducing a negative, and now we're back to integrating from a to b. And we can switch this to polar form just by taking the absolute values of all this in here. So absolute value of t plus I epsilon minus a to the pth power, and then same deal over here. We're going to have b minus t plus I epsilon to the 1 minus pth power, and then this is the modulus, and then we also have the argument, which is up over here. So we're going to have e to the I, and I'm not going to write all this out, but we're going to have basically arg of f, so e to the I, I'm just going to write it as arg of f, like so. But imagine you're replacing z's with all these t plus I epsilons. And now what we're going to be doing is we're going to let epsilon approach 0. And what's going to happen as epsilon approaches 0? Well, on the integral, we're going to have the integral from a to b. These epsilons will basically disappear, leaving us with t minus a to the p, and then b minus t to the 1 minus p. And then over here, since we're approaching everything from above, so imagine this line over here get closer and closer and closer to the branch cut, we're going to consider what happens to the argument as we approach the interval a to b from above. And what's going to happen to the argument? Well, it's just going to turn into this thing which we've written up here. So that's why I kept it there. So we're going to have e to the I, and then the argument will approach 1 minus p times 2 pi, like so, and then dt. Alright, cool. And now this is equal to, well, notice on the interval a to b, these absolute values are irrelevant because we're going to be positive everywhere. And we can bring up this factor, or this constant, so that we're going to have e to the 2 pi I times 1 minus p, integral from a to b of t minus a to the p, and then b minus t to the 1 minus p dt. But notice this integral is the exact same integral we started off with, we just have different variables, and I forgot to call this integral I, so let's do that. So this integral is now I, so we've basically solved our first integral, so this is I over here. So in the limit, as epsilon approaches 0, our sine one turns into this complex exponential function times I. So this is going to be equal to e to the 2 pi I times 1 minus p times I, like so. Alright, now let's do the exact same thing to side 2. So side 2, but instead over here we're going to have a minus epsilon, and t is now going to the right, so we're going to have a to b, and then of course dz is going to be equal to our dt. And now again we're going to plug everything in. I'm just going to rush through this because it's going to be very similar to what we had before. So we have the integral from a to b, and then t minus I epsilon minus a to the p, and then b minus t minus I epsilon to the 1 minus p dt. And writing this in polar form, we have the integral from a to b, absolute value of all this junk over here. So absolute value t minus I epsilon minus a to the p, that should be a straight line, and then absolute value of b minus t minus I epsilon raised to the 1 minus p, and then we also multiply by e to the I arg of f dt. And as we approach from below, so as epsilon approaches 0, this thing, arg of f, as we approach from below, we're going to approach 0, an angle of 0. So we're going to have the integral from a to b. We can remove those absolute values like before. So we have t minus a to the p, and then b minus t to the 1 minus p, e to the I 0 dt. but e to the I0 is 1, so this is going to be exactly I. So psi 2 in the end is going to approach I. So we're going to have a plus I, and I believe I forgot a negative sign over here. There should have been a negative sign on psi 1, because remember we had to switch the orientation of the in-school. I probably left it off somewhere in the working out, but you guys can probably go back and check out where I missed that, but there should be a negative there. Alright, so those are two integrals down. Let's go to the integral over gamma 1 now. So integral over gamma 1 of f of z dz. We're going to introduce yet again another substitution. So we're going to be letting z be equal to, now what exactly is gamma 1? It's a circle that's centered around A. So we're going to start at A, and then we're going to add, let's call this a radius over here, epsilon. Once again, it really doesn't matter because it's going to approach 0 in the end anyways. So we're going to have an A plus epsilon e to the I theta. And what are our theta values? Well, we're going to start somewhere near here and then end all the way over here. So we're going to start pretty close to 0, and we're going to end pretty close to 2 pi, but in the end we're taking the limit anyways, so we can just consider theta to be on the interval 0 to 2 pi. It's going to work out the same way in the end anyways. And of course our dz is going to be equal to, well, differentiating this using some chain rule, is I epsilon e to the I theta d theta. Alright, cool, and let's plug everything in. So we're going to have now the integral. Now we're going to from 0 to 2 pi. And now we're going to have, now plugging a plus epsilon e to the I theta into these z's. Well, first of all, on this first factor, minus a and positive a will cancel each other out, leaving us with epsilon to the p, and then e to the I theta p on the inside. And then for the second factor, no cancellations really, but we're going to have minus z, which means we're going to have b minus a minus epsilon e to the I theta raised to the 1 minus p. So that's a second factor, and then dz, we know that turns into I epsilon e to the I theta d theta. And what we want to do now is when we want to estimate this integral a little bit, we want to show it's equal to 0 in the limit. So let's take absolute values everywhere actually. So taking absolute values everywhere, and now we can use the integral inequality to say that this is less than or equal to the integral of the inequality. So bringing these inequalities inside the integrand. So now we're going to have the integral from 0 to 2 pi. Absolute value of the epsilon to the p is, well, just epsilon to the p. We also have an extra epsilon over here, so let's combine those together. So epsilon to the p plus 1. And then absolute value of this complex exponential function is just 1. Absolute value of I is 1. Absolute value of this other complex exponential function is also 1, leaving us with just the absolute value of b minus a minus epsilon e to the I theta to the 1 minus p times d theta. Okay, now we want to estimate this integral even further, because notice this integral is bounded above by the maximum value of whatever's in here. So if we can find the maximum value of whatever's inside of here, we've basically found another upper bound for our integral. So what is the maximum value over here? So we can say that this is less than or equal to the integral from 0 to 2 pi, epsilon to the p plus 1, maximum, as theta varies along 0 to 2 pi, of this absolute value thing. Where exactly does the maximum happen? Well, where is b minus a? Well, if you drop the complex plane, b minus a is some positive real number. And if you're adding or subtracting, in fact, epsilon e to the I theta, you're just constructing some kind of circle around it of radius epsilon. And the maximum value of this absolute value is this furthest point away from here. So you're basically taking b minus a and you're adding an extra epsilon. So this is in fact equal to the integral from 0 to 2 pi epsilon to the p plus 1, and the maximum value of this thing occurs at b minus a plus epsilon, and then this is raised to the 1 minus p d theta. That's an ugly theta, looks like a sigma, so d theta. All right, very nice. And notice that we've always found an upper bound for this original integral, which means that our original integral is bounded above by what we have right now. And this is really easy to evaluate. This stuff's just a constant, so it just jumps outside. And we're integrating from 0 to 2 pi of d theta, which is just the length of the integral. So now this is less than or equal to 2 pi times epsilon to the p plus 1 b minus a plus epsilon to the 1 minus p, and we're taking the limit as epsilon approaches 0. So taking the limit on both sides, we can see that the limit as epsilon approaches 0 on the absolute value of the integral over gamma 1 is going to be less than or equal to 0. So this thing definitely goes to 0 under the condition that p plus 1 is positive. So we need this condition right here, because if p plus 1 is negative, then you actually blow up and diverge. So p plus 1 is positive, which implies that p is greater than minus 1. So that's actually the first condition to what we have over here. So p is greater than minus 1. I guess I'll just stick it over here because we can discuss this later. And just by the squeeze theorem, of course, since this is an absolute value, it has to be greater than or equal to 0 as well. So squeeze theorem applies, and obviously limits as epsilon approaches 0 on the integral over gamma 1 is going to end up being 0. So in the limit over here, we're going to end up with 0. All right, now we're going to do the exact same thing for gamma 2. It's going to be very similar, but just a couple tweaks here and there, I guess. So the integral over gamma 2 now are centered around b. We still have the circle of radius epsilon. dz is still the same thing, but theta is going to go from what we're starting here, and we're going all the way up. So our theta will be between minus pi and pi, like so. So plugging all this stuff in, we're going to have the integral from minus pi to pi of b plus epsilon e to the I theta minus a. That's the first factor. Then for the second factor, notice that positive b, and then since we're subtracting, we're going to have a b minus b, which will cancel each other out, leaving us with minus epsilon e to the I theta to the 1 minus p power. And then dz is going to become I times epsilon times e to the I theta d theta. This is still in absolute values. Again, we can use the integral inequality to bring the inequalities inside the integral, leaving us with the integral from minus pi to pi. Absolute value of this thing, let's just kind of leave it as it is. So absolute value of b minus a plus epsilon e to the I theta to the p. Then absolute value of the second part over here, well, we can drag the absolute values inside of this power, and this e to the I theta, absolute value of that is just going to be 1, leaving us with just epsilon to the 1 minus p. And then we also have an extra epsilon over here, so we're going to in fact have 2 minus p. Absolute value of I is 1, absolute value of this complex exponential function is also 1, and then we have a d theta. And again, we want to find the maximum value of this absolute value. So b minus a is again over here. Maximum value will be b minus a plus epsilon, which lands us at this point on the circle, which is the furthest away from the origin. So this is now bounded above by the integral from minus pi to pi. Now we're going to have epsilon to the 2 minus p times b minus a plus epsilon to the pth power d theta. And this is very easy to evaluate. It's going to be equal to 2 pi epsilon to the 2 minus p b minus a plus epsilon to the p. And then as epsilon approaches 0, this is going to be 0 in the end anyways, provided that this 2 minus p is positive. And if this is positive, this implies that, let's subtract 2 on both sides. So minus p is greater than minus 2. Dividing everything through by negative and switching the signs around, p is less than 2. And that's in fact how we get to this condition over here, that p is bounded between minus 1 and 2, not inclusive of those endpoints. So this integral in the limit will be less than or equal to 0. So it's going to be equal to 0 in the end anyways. So this is going to be equal to 0. Alright, so we've evaluated all 4 of those integrals. So now for the tricky part, which is evaluating the residue at infinity. This is probably my favorite part of this whole entire integral. So let's get rid of this picture as well. We don't really need it anymore. So step 4 is the residue calculation. So residue like so. Alright, so let's box this over here because that's its own separate thing. And now we're going to be calculating the residue at z being equal to infinity of our function f of z. And remember, the way we calculate the residue at infinity, we can just calculate the residue at z being equal to 0, but we have to make a couple modifications to our function. First of all, we have to divide by minus 1 over z squared, and then we have f of 1 over z like so. And that's going to give us the exact same result. Okay, so now let's just plug the definition of f of z into this formula. So now we are going to get the residue at z being equal to 0 of minus 1 over z squared. F of 1 over z, well, we just plug 1 over z into all these z's over here. And we're going to have 1 over z minus a to the p. And then b minus 1 over z to the 1 minus p, like so. Okay, and now what I want to do is I want to get everything in here on the common denominator. So if we do that, we're going to have the residue at z equals 0 of minus 1 over z squared, and then 1 minus az over z. So multiplying this a by z over z, this is raised to the pth power, and then multiplying this b by z over z, we're going to have bz minus 1 over z to the 1 minus p. And now we can split this power between the numerator and the denominator. So we're going to have on the numerator 1 minus az to the pth power, and over here b minus 1 to the 1 over p, and on the bottom we also have z to the p and z to the 1 minus p. Alright, and notice on the denominator we have z to the p times this z to the 1 minus p. Multiplying those together, this p and this minus p will cancel each other out, leaving us with just the z on the denominator, which we can use to combine with this minus 1 over z squared to give us the residue at z equals 0 of minus 1 over z cubed. And now we have 1 minus az to the p. And I also want to make a couple modifications to this second factor over here. Notice we have minus 1. I want to turn that into a 1 somehow by introducing a negative inside of there. So ideally we want kind of like a minus or 1 minus bz, just to make things a bit cleaner. So this is raised to the 1 minus p. So these two are still the same thing, but notice minus 1 is the exact same thing as e to the I pi in polar form, and then we can distribute this power into everything. So this is going to give us e to the I pi times 1 minus p. So we're going to have up here now e to the I pi times 1 minus p, like so, and we're just left with 1 minus bz raised to the 1 minus p. Okay, very good. And the reason why I chose to put everything in this form is because we're going to be using some binomial theorem right now. Because notice that we have fractional powers which are a little bit hard to deal with, especially if we're calculating a residue. If we can express these using some power series using the binomial expansion, then we're going to have a whole number multiples of the z, which we can form some kind of Laurent series from, and from there we can directly deduce the value of the residue. Okay, so let's do that now. Recall the binomial theorem. If we have x plus y to the pth power, and this is for the generalized binomial theorem, so we're assuming p is a fractional power as well. This is equal to the sum running from, let's use an index k, from 0 to infinity of p choose k times x to the p minus k, and then y to the kth power. So when you're dealing with fractional powers, you have to go all the way up to infinity. You don't just stop at p because it doesn't really make sense that way. So let's apply that to both of these factors. So now we have the residue at z being equal to 0 of minus e to the I pi times 1 minus p divided by z cubed. And now for the first factor, we're going to have the sum running from k going from 0 to infinity of, now we have p, choose a k, and then x is exactly 1, and 1 raised to anything is just 1, so that's why we wanted 1 at the front over here. So we're going to have 1 and then minus az raised to the pth power. That's the first factor, and now let's do the same thing for the second factor. So now this is going to be the sum running from j equals to 0 to infinity of p choose j, actually 1 minus p choose j, because we have a power of 1 minus p, and then we're going to have a minus bz raised to the jth power, like so. This should have been the kth power actually. We raised it to the index. So that's all. And now comes the really interesting part. We don't really want to expand out these sums. We don't want to multiply them together or anything. That's just going to take way too long. Because with the residue as e equals 0, we're only interested in the coefficient of the 1 over z term. And notice we have a 1 over z cubed term at the front, which means that whatever polynomial, so this is going to be some kind of power series actually, whatever power series this becomes, we're only interested in the z squared terms, because z squared will cancel out with the z cubed to produce 1 over z. And if we can figure out what the coefficients of z squared are from this whole polynomial or power series, we can basically recover the residue from there, which is quite nice. So our goal now is to figure out how I can get a z squared from this product of two power series. And we can do that by considering a couple of cases. So first of all, we can have that k is equal to 0 and j is equal to 2. Because notice if we have z to the 0 over here and z to the 2, and if we multiply them together, we're going to get a z squared term. We also have the case where k is equal to 1 and j is equal to 1. So we're going to have a z to the 1 and a z to the 1. Multiplying those together, we're going to get a z squared. And we also get the case that k is equal to 2 and j is equal to 0. And again, we're going to get a z squared term at the other end if we take that case. So we have three separate cases that we have that will produce a z squared. And once we plug in these k and j values and then multiply them together and everything, we're going to add them up, because if you imagine yourself expanding this power series out, you're going to get a couple terms that have a z squared in them, and then in order to calculate the coefficient of the z squared, you just add them together. So grouping them together, that's why we're going to add everything together at the very end. So our goal is now to compute each of these terms of the separate power series, and then we're going to multiply them together respectively, and then add them together. And I guess we'll just do that using a table to kind of present things nicely. I'm going to rub this stuff out. So the residue at infinity is basically what we have down here. So what we have so far is equivalence. And now we're going to go through each of these cases. So let's take a look at where k is equal to 0. If k is equal to 0, then we have p choose 0, and then minus a z to the 0th power, which all evaluates to 1. So when k is equal to 0, we have 1. How about when j is equal to 2, so this second column? Well, we're going to have 1 minus p choose 2, and we're going to figure out what that is equal to later on. And then we're going to have minus bz squared, but that's exactly b squared times z squared. Alright, great. Let's take a look at when k is equal to 1 and j is equal to 1. When k is equal to 1, we have p choose 1, but anything choose 1 is that something itself, so it's just going to be p. And then minus az to the first power is just minus a and z. So we have minus a times p times z. And then when j is equal to 1, well, we're going to have something similar. We're going to have 1 minus p choose 1, which is 1 minus p. And then we're going to have a minus b times z. So minus b times z, like so. Alright, so that's the second row done. Let's take a look at the third row. So k is equal to 2. What happens there? We're going to have a p choose 2, like so, and then everything here is squared, so we have a squared, z squared, and when j is equal to 0, well, this whole thing just becomes 1. Alright, so we have all of that stuff figured out. Let's figure out what happens when we multiply everything together. Well, on the first row, we're just going to have 1 minus p choose 2, b squared, z squared, and on the second row we have, well, these two negatives cancel each other out, leaving us with abp 1 minus p times z squared. And on the third row, well, we just simply have a p choose 2 times a squared times z squared. So those are all the coefficients of the z squared terms, and now we just have to add them all together to figure out the total coefficient, I guess. So we're just going to have 1 minus p choose 2 times b squared plus abp times 1 minus p plus p choose 2 times a squared, and this is basically the whole entire coefficient of our z squared term. All right, very nice. So what did we just find? We found that if we consider this whole thing to be a power series, if we just extract the z-squared term, this is what we are going to get. So this thing is equal to the residue at z equals 0 of minus e to the I times 1 minus p, and then we have a z cubed, but notice we also have a z squared over here, which will kind of cancel each other out, so we have divided by z, and then within this power series, I guess we're going to have the dot dot dot, and then we're going to have whatever's inside. Let's just call this coefficient over here capital A, I guess, so capital A, and then plus higher order terms. And notice this function in here is in fact centered around 0 because we only have a z down here, and at 0 there's a pole. So the residue at z equals 0 of this function is just the coefficient in front of the 1 over z term, which just happens to be minus e to the I pi times 1 minus p, multiply that by a. Alright, so we've basically calculated the residue at z equals to infinity, so this stuff was all equal to the residue at z equals to infinity. So the final value for the residue at z equals to infinity is going to be equal to, well, we have a minus e to the I pi times 1 minus p, and our a over here was precisely a squared times p choose 2 plus b squared times 1 minus p choose 2, and then we add a times b times p times 1 minus p. Alright, so now what I want to do is I want to simplify this residue a little bit by getting rid of the p choose 2 and the 1 minus p choose 2. So this is a little bit tricky to do because p is a fractional, so it's not necessarily a whole number, so we can't really use the usual n choose k is equal to n factorial over k factorial times n minus k factorial. We have to use a bit of an alternate expression, because if n is fractional, if n is equal to p, for example, then the way we do this is, well, we look at p factorial divided by p minus k factorial, and if you do enough manipulation, you'll find that you'll get something like p times p minus 1 times dot 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 times p minus k plus 1 divided by k factorial. And the thing on the numerator, that's what's called the falling factorial, so it's p, and then we denote the falling factorial by k with a little bar underneath, and this is divided by k factorial. So this falling factorial, it's basically the usual factorial, so we take off 1 each time we multiply, but we stop when we hit k plus 1. So if we have a p choose 2, we're going to have p, and then we're going to subtract 1, so p minus 1, and then dot dot dot, and then p minus 2 plus 1, like so. And this is divided by 2 factorial. So if we have 2 down here, we stop at minus 2 plus 1, but notice minus 2 plus 1 is exactly minus 1. So in fact, we're supposed to stop right over here. So p choose 2 is exactly p times p minus 1 over 2 factorial, which is 2. And we can do the same thing for 1 minus p choose 2. So 1 minus p choose 2 is equal to, well, we start off with 1 minus p. So 1 minus p, and then we just take off 1 from it. So that's going to become minus p, and we stop there. So I guess a general pattern you could look for is whatever number down here is the number of factors you should have on the numerator. So this is divided by 2 factorial, which is 2, and this is equal to minus p times 1 minus p divided by 2. And we can plug all of that in. Let's move over down here. This is now going to give us minus e to the I pi times 1 minus p, and then we're going to have a squared. P choose 2 is going to turn into, well, 1/2, and then p, and I'm going to write p minus 1 as minus 1 minus p, and we'll see later on why. So we're going to introduce a minus, and then we're going to have a 1 minus p. And then 1 minus p choose 2. Well, we're going to have a negative here, so minus, and then also a half, and then we're going to have our b squared, and then we're going to have p and 1 minus p. And then finally we have ABP times 1 minus p, so we'll just keep that as it is. So ABP and then 1 minus p. Alright, very fine, and now we can notice that we can factor out a couple of things, and most noticeably this p times 1 minus p. So if we factor that out, we get a minus e to the I pi 1 minus p, and then p times 1 minus p. And then notice we have this half factor everywhere, but we're kind of missing a half factor over here. So let's introduce 2 over 2, so plus 2abp divided by 2. That way we can factor out a half as well. So now we can factor out 1/2 over here, and then we can also factor out a negative out of all these terms, which will cancel that out here, which is quite nice, leaving us with just a squared minus b squared, and then plus 2ab is what remains, because we factor out a p of 1 minus p as well as a 1/2. Alright, very nice. And notice this part over here, that's basically the binomial expansion. So we can simplify this down to being e to the I pi times 1 minus p divided by 2 times p times 1 minus p. And then this part over here, that just simply becomes a minus b squared. So a minus b, but the whole thing's squared. Alright, very fine. So we've basically calculated the residue at infinity. It's going to be exactly this thing over here. And now it's time for step 5, which is the grand finale, putting everything together. So step 5, we'll just call it the grand finale. So first of all, we have this minus 2 pi I times the residue at z equals to infinity. So we have minus 2 pi I. Residue at infinity, we found it to be equal to this expression over here. So that's equal to e to the I pi 1 minus p divided by 2, and we have p, 1 minus p, and then a minus b squared. But I'm actually going to write this as b minus a squared. It's the same thing. It's a bit nicer because b is bigger than a. And we found that this is equal to the sum of all these integrals, but notice we have a 0 here, we also have a 0 here, and what really remains is this I, and we can factor out an I here as well. So we can factor out an I, and then we're left with 1 minus e to the 2 pi I, and then we have a 1 minus p. Alright, this is quite nice, and what I want to do now is I want to bring this negative over to the other side and switch the order of the terms inside of this bracket. So now we have a 2 pi I times e to the I pi 1 minus p divided by 2 times p times 1 minus p times b minus a, but the whole thing squared, is equal to I times e to the 2 pi I times 1 minus p, and then minus 1. Alright, very fine. And now notice that we can bring this e to the I pi 1 minus p onto the other side. And we're going to do so by multiplying both sides by e to the minus I pi times 1 minus p. So I guess I'll just put this in red over here. We're going to multiply both sides by e to the minus I pi 1 minus p. Multiply that over here as well. And what that's going to do, we're going to cancel this and this out over here, leaving us with 2 pi I times 1/2 times p 1 minus p times b minus a, but the whole thing squared, being equal to I. And now if we distribute this into this bracket, notice that we have a common factor of pi times I times 1 minus p. So we have left 2 minus 1, which is exactly 1. So we're going to be left with e to the I pi times 1 minus p. And for this one, well, that's pretty easy. We're going to have minus this thing. So minus e to the minus I pi times 1 minus p, like so. Alright, and notice the reason why I did this is because this basically looks like the complex exponential definition of the sine function. We're just missing a division by 2i. So let's go ahead and divide both sides by 2i. We have a 2i waiting for us nicely on the left-hand side over here. So if we do that, we're going to be left with pi divided by 2. So pi divided by 2, then we have p, 1 minus p, b minus a, but the whole thing squared, being equal to I, and now this whole thing is going to become the sine function. So we're going to have sine, and the sine of what? Well, we have I times some pi times 1 minus p, and then we have pi times 1 minus p over here as well. So that's going to be sine of pi times 1 minus p, like so. And notice one thing over here, we can expand out what's inside of this sine. So we have now sine of pi minus pi times p, but there's a nice identity with the sign. You can kind of think about this as translations. This is going to give you the exact same thing as sine of a pi times p. So we can do that replacement over there. So this is exactly equal to I times the sine of pi times p. And all that's left to do is to divide both sides by sine, or multiply by the cosecant of pi p, if you want to do it that way. So we find that I is equal to pi over 2 p 1 minus p b minus a, but the whole thing squared, times the cosecant of pi times p. And that is the final result for today's video. We've found the value of I, which is exactly the integral we started off with. So there you have it. That is the generalized result for this integral. This is really quite nice. You can evaluate a lot of integrals that way. And notice, as I was saying at the very start, the reason why we exclude 0 and 1 is because, well, if you plug those p values into this cosecant, you're going to be undefined. But in fact, if you take the limit on the whole entire thing as p approaches 0 or p approaches 1, then you in fact get a finite result. So I guess this formula only works excluding 0 and 1, but the integral converges including those 2 points anyways. So that is pretty much it for today's video. I hope you guys enjoyed it. Make sure to subscribe for more content like this in the future, and up until next video, hope you guys have a wonderful day, and I'll see everyone later. Bye bye.